Okay, so our next speaker is Serhii Myroshnychenko, who will talk about how far apart can centroids be. Please go ahead. Thank you.
Thank you very much. Thank you very much for organizing this and for the introduction. So today I would like to talk about the joint work with Katerina Tatarko from University of Waterloo and Vlad Yaskin at the University of Alberta. And although we are in Canada, but it's a big pleasure to be with you today. I would like to start by defining centroid of a convex body. So you already heard from Dima's talk about the notion of convex bodies, and the centroid of a convex body would be the following notion. I'll write it down and then I'll explain it. All right, so what do we have here? We have volume of a convex body, 1 over that, times the average of the coordinates of the points inside of the convex body. So let me just add here that K is the convex body, which is the compact convex set with non-empty interior in Euclidean space, and N will be at least 2 to make things more exciting. All right, so this is the, again, the centroid of a convex body. It's a special point, and convex bodies in general have quite a few interesting points. So what we were wondering about, the relation between those points. And let me introduce another point with like where we're measuring the distance to. So what we're gonna do, we're gonna look at our convex body. Let me write it and draw it like this. This is our K, it's 3-dimensional. And we're gonna project it on a 2-dimensional, let's think about 3-dimensional space right now, but in general, it also works. I'm gonna take a just 2-dimensional subspace maybe, or hyperplane H, and just gonna project it on the plane. One of the nice properties of convex bodies is that, of course, projection will remain convex as well. So let's call this projection on H of K. So this is our second creature, and the second creature also has a centroid, right? So let's start here somewhere. Maybe this is my C of K, and this guy, as being a convex body in 2-dimensional space, also has its own centroid. Right? Notation becomes a little lengthy, but I should be clear that this is just the centroid of the projection. So what we're gonna ask ourselves today is how far apart those two guys can be. Well, not vertically, because, well, it doesn't really make sense. But if we project this point on the same subspace, these 2 points now are in this plane. And what we're wondering about is how far apart those 2 guys can be. So let me make it more official and talk about some technicalities to make this question well defined. All right, so the question is, what is the smallest constant D and yes, it depends on dimension. So right now we're talking about D3, such that for any convex body K, we have the following. Well, let me write, it lives in En, of course. We have the following. So the distance between the projection of the centroid, this is the second point, it's right here, minus the centroid of the projection. I'm talking about this second point here. How far apart can they be? So again, the way I formulate it now, we should be careful because we can scale our body and projection will scale accordingly, and the distance can become very, very large. So we should do this measurement with respect to some internal parameter of the body. And what we did, we compared it with the width of the convex body that you heard during the previous talks that the width is basically this distance, right? We draw parallel lines and we measure the distance in between those two lines. So this is going to be the width of the convex body K in the direction of U, and U is a vector that parallel to the line passing through these 2 points. So let me finally finish dn times, and this is the question we're wondering about. So simple observation is that if your convex body is centrally symmetric, as we heard in Dima's talk, such bodies are very common. Right, if you take, there is a point inside such that if you take a point on the boundary and reflect it, it will be on the boundary as well. So this is k is equal to negative k. Then this distance that we're wondering about, right? Then the distance in question is 0, right? Because simply the centroid of the projection of the centroid end up at the same point. So in some sense, what we're wondering here is some kind of measurement of non-symmetry of the convex body. So let me not keep you wondering about the answer for too long. Let me give you the answer in R3, and then we'll talk about a few steps of getting that answer. So I guess theorem. I guess 2022 probably. The answer, one of the optimizers, the bodies for which this maximum distance is attained, will look like this. It's actually going to be quite interesting structure, I think. I don't know, I find it interesting. So we're going to start with a trapezoid in two-dimensional space. Trapezoid with equal sides, very symmetric. I'll give the coordinates of the points very soon. What we're going to do after, we're going to, above the smaller side, we're going to bring it up a little. Let's see, somewhere here. And we're going to connect these points with the rest. And this is one of the most symmetric, in some sense, optimizer of our question. So what are the coordinates? Let's assume that this is our second coordinate, x2. Somewhere in the middle, we have x1. And x3 goes like this. So this point, just so we have it, is the point. This one, please note that vertical scaling doesn't really change the value in our question. So, but we can make it height 1. So as I said, this point and this point are symmetric with respect to the x1, x3 plane. So, with the minus. And this guy is simply 0, 1, 0. And it's intuitively clear why this should be the answer, because if you look at the projection, the mass, the volume of the projection is more to the left, and the volume of the body is more to the right. Right? So we're kind of pulling it apart, and that's why the centroids are processed away. But again, this is just hand-waving answer. So this is the structure. And finally, what is the distance? The distance, so in our case, it's d3. It's 1 minus square root of 2 over 3. Very nice number. Of course, remember that we're doing it with respect to the width. So in this creature, the width is 1. Right? So the distance is in there between the points, somewhere here and here. Okay, so in the remaining time, I'm not able to talk about every detail, of course, but I would like to talk about the analogous question in R2, in two-dimensional Euclidean space. We can solve it together, and then I'll talk about one of the key ingredients of the proof for three-dimensional case and higher dimensional case as well, it's actually quite fascinating too. So let's do it rather quickly in two-dimensional space. So what we have a convex body, right? It's somewhere here, it's just flat, and we are projecting it on a line. Of course, it's going to be a segment. Our projection will be a segment, and we do know what the centroid of the segment is. It's a point right in the middle. All right, so now we're wondering how far away can the second center fall. And again, let's make it 0, 1 for simplicity. So our first step will be the so-called Blaschke shaking. So we're going to shake our body. How do we shake bodies? We consider, in this case, segments orthogonal to our chosen direction. We pick middles of those segments and we bring them down. So when we bring them down so these points fall exactly on the fixed line. So in other words, we create a guy that looks symmetric with respect to this line, still with the same width. Okay, so this is the first step. The second step would be to move the mass somehow. So to move the mass, let's look at two vertical lines like this, and let's choose the line passing through this point so that it cuts out, and let me draw it better. So it cuts out our body in such a way so that volume on this side is equal to the volume of this side. Oh, sorry, every time I make this mistake, sorry, this side over here. I want this, to be far apart. So we can always do it, right? Because we're continuously changing it. Eventually somewhere there will be equal volumes. Okay, so when we do that, we obtain our answer pretty much, because now we end up, well, you can do the same on the bottom, the same thing. We end up with a triangle like this. So of course, the point here will be 2/3, and point here will be 1/2 somewhere. So the distance in two-dimensional case, 2/3 minus 1/2 is equal to 1/6, which is approximately, there's a reason I'm writing decimals to show you how it changes in R3. So the same trick will not work exactly the same way in three-dimensional and higher cases, because you don't have just one measurement. You also need to take care of the sides somehow. So nevertheless, the first few steps in the proof of three-dimensional case are actually similar, right? So I don't have that much time, so let me just get to the point. So in terms of first step, so we use symmetrizations. So first we're going to use Blaschke shaking. We're going to shake it with respect to plane. So we're going to obtain something like this. Sorry, let's draw it. And something similar on the bottom. And the second symmetrization we're going to do it with respect to a vertical plane. So that, again, not a good picture, but you symmetrize it with respect to the vertical plane. And this is x1, and this is x3. This so-called Steiner symmetrization sometimes. Right, so you're kind of trying to push this distance onto the x1, right? You're trying to, the distance should be exactly along the x1 coordinates. Symmetrizations help with that. And the last part that I will manage to talk about, and which is the next step in the proof, deal with the projection. Because after this, steps that kind of preparational, symmetrization, etc., shrinking, stretching, you have two components. You have the projection that you have no clue about, and you have the so-called, not so-called, the surface above it, which is the roof in some sense. So what we're going to do now, we're going to deal quickly with projections. I won't take too much time. After all these preparations, the picture in the plane looks like this. So this is 0, 1. It looks something like this. I don't know. Symmetric with respect to this line. So what we're going to do now, we're going to find a line that splits, that's not a good one, that splits our volume, or area rather, of the projection into areas, equal areas. This and this should be equal. There are many lines like this, right? For any direction, I can find a line like that. So this is what I do first. Among all of those lines, there are very, very many as points on the circle. I choose, now I build a plane right above it. So this plane right above it does the same thing to the body and splits it into volumes of the same volumes. I can always find such a plane. So in other words, there exists a line in the plane of the projection and a plane perpendicular, right? I mean, passing through this line kind of orthogonal to that plane, such that the plane split the body into pieces and the area into equal pieces. And then I can repeat. And what do I mean by that? I mean the following, that if your picture looks like this, and you find the right line and the right plane, this guy should be equal to this guy, right? As I just said earlier. But then, after not very difficult considerations, you can repeat the same thing for each of them. And what you observe is that your projection shouldn't be actually curvy. It should be actually flat on sides. So you end up with a picture like this. And then again, after not so long consideration, not such long considerations, you end up cutting out these curvy pieces and you see the trapezoid that should be in the projection. And dealing with the surface above it is a completely different story. I would not be able to discuss it, but that approach is more analytical and also interesting. So before I stop, let me just say that there are many questions similar in nature to this one, right? There are many different points of a convex body, and measuring how far apart they can be is, I find, quite curious. So thank you very much. Thank you for doing this, and Slava Ukraini.